Perhaps the pinnacle of scientific achievement is the fact that, at a fundamental level, from subatomic scales up to the largest cosmic ones, humanity has come to understand the universe more completely and comprehensively than ever before. The standard model of particle physics accounts for the interactions, presence, and properties of normal matter and radiation in the universe, including atoms, ions, light, and neutrinos, while general relativity accounts for gravitation. Cosmically, the Big Bang plus the ingredients of inflation, dark matter, and dark energy explain the universe's evolution and structure, allowing us to piece together the most powerful explanatory picture of our cosmos ever concocted. But you wouldn't know it by reading the news about science these days. Headlines often make it seem like our understanding is constantly being overturned. You'd think that dark matter, dark energy, and inflation were all ad hoc fixes destined to be wrong, that astronomy discoveries about distant galaxies, cosmic expansion, and black holes have demonstrated that our view of the universe is fundamentally broken, and that new scientific discoveries continuously disprove our concordance picture. What about this? New study, where no cosmological law has been breached to declare that dark matter and dark energy do not exist. The study, like many of its kind, claims that dark matter has been debunked and the universe is twice as old as we presently think. Rather than focus on the specific claim made here, it's more instructive to show you how theoretical physics works, and what articles making claims such as these are really saying. Science is an ever-evolving field. Theories are constantly tested, and new data can either reinforce or challenge our current understanding. This iterative process is what makes science so robust. When a new study comes out, it doesn't instantly rewrite the textbooks. Instead, it adds to the body of evidence that scientists use to refine their models and theories. The question often arises, why do scientists invest time in ideas that seem destined to fail? The answer lies in the core objective of science, to challenge and rigorously test our understanding of the universe. The number one goal of a scientist, even though we don't normally think of science in this fashion, is to try and absolutely annihilate any idea about how the universe works by throwing every imaginable test at it. All it takes is one irrevocable failure and the theory will crumble, falling to pieces. It's only the strongest, sturdiest theories that can hold up to every test that we can conceive of that stand the test of time. Newtonian gravity predicted everything we were capable of observing until we had centuries of precise data, showing Mercury's orbit deviated from Newton's predictions by just 43 arcseconds per century. Einstein's general relativity continues to successfully predict the behavior of every object within space-time, our longest-standing fundamental theory at this time. The Standard Model, completed either in the 1960s or 1970s, dependent on whether you consider electroweak theory or quantum chromodynamics the completion moment, has been tested more thoroughly than any theory ever, and no experiment has ever contradicted its predictions. But the theoretical journals burgeon with papers that talk about alternatives to, modifications to, or extensions of general relativity and/or the Standard Model. It may seem puzzling to an outsider. If science is our best model of reality, why would we spend time, or in the eyes of many waste time, investigating ideas that are clearly wrong, and that clearly can't even replicate the successes we already know the current theories can successfully explain? It's because long-term, we want our theoretical understanding of the universe to advance beyond our current models and frameworks. Cosmological inflation, one of my favorite examples, began as an idea that, yes, could explain several important puzzles that the Big Bang without inflation could not. But it could not even reproduce a universe that was homogeneous and isotropic. The same on large scales in all locations and directions. We had known our universe was homogeneous and isotropic for decades before the idea of inflation was first put forth, and the first model, now known as old inflation, failed spectacularly in this regard. But inflation was a brilliant idea with a lot of potential, and it required years of theory development by many of the most gifted and most educated minds in the field at that time, before it could clear all three of the necessary hurdles to becoming a serious, fully fledged theory. Most theorists who work on alternative cosmologies or alternative physics ideas today are working in relative isolation and obscurity. and we are well aware that our current picture of the universe is unlikely to be the ultimate, final answer given how many things we still don't fully understand. So what is actually true? It's true that if you restrict yourself to one singular aspect of the universe, such as what happens if I plot a graph of object distance versus redshift, or what do I see if I look at the rotation curves of galaxies, or what conclusions can I draw if I look at the temperature fluctuations in the cosmic microwave background, or some other relation in isolation, you can find many plausible interpretations of that one aspect of the data. There are many varied cosmologies, not just the consensus cosmological picture, but wild alternatives that can reproduce any one of these observations, or sometimes even 2 or 3 such observations all at once. But they normally fail for some other spectacular reason. You can modify gravity to reproduce rotating galaxies, for example, but you can't explain the large-scale structure of the universe and the fluctuations in the cosmic microwave background without either an additional modification to mimic dark matter or by adding some type of dark matter as well. You can explain the fluctuations in the cosmic microwave background with a large amount of spatial curvature with very different ratios of dark matter and dark energy to the consensus model, but only if you include an unrealistic value for the universe's current expansion rate. And you can reproduce the redshift distance diagram with a much older universe that has the fundamental constants all vary together, but only if you ignore a whole suite of observations that have been made in laboratories here on Earth. The key to a successful scientific theory is to hit upon a theory that can account for what we refer to as the full suite of relevant observations, not just a few cherry-picked examples. If even one set of observations or experiments conflicts with what the theory predicts, the theory is false. It's why, when Einstein was informed about the 1931 publication of the book 100 Authors Against Einstein that claimed to disprove general relativity, Einstein simply responded to the collection of anti-relativity essays with a simple quip. To defeat relativity, one did not need the word of 100 scientists, just one fact. In other words, just one example of how the theory fails when compared to reality is sufficient to show that the theory, in fact, does not adequately describe reality. The consensus models that we have, the standard model of particle physics and the standard model of cosmology among them, only thrive as the consensus model because of how compatible they are with explaining the full suite of observations. The alternatives that you see, practically every one of them, is merely an example of a theorist or set of theorists playing in the proverbial sandbox, working with a toy model of reality to try and develop a theory in its infancy. We do this because we recognize the importance of being open-minded and exploring everything we can. But we must always come back to reality and its cold, hard constraints. Whenever we fail to do that, we abandon science for our own wishful thinking.